we discuss in this video about the strengths and the weaknesses of decision tree, and we are going to spend a little bit of time on tree pruning, which addresses maybe the biggest weakness of decision trees, that is that they tend to overfit. But here is a comparison between some of the key strengths and some of the key weaknesses of decision trees. So if I start with the strengths, the reason why they are indeed in practice very popular is that these are interpretable models. And when I say interpretable, I mean that they are very close to the way humans make decisions. And if you look at the decision tree and you check the queries that are being made in the internal nodes, they are very easily translatable into insights into your data set. So for example, if the decision or the query was, hey, is age smaller than 40 or is it higher than 40? That's something that is easily translatable and easily human interpretable. So that's a big advantage. I have here written in principle, because this advantage, even though conceptually it's clear, is going to disappear if you have huge trees, because you have to follow the entire decision path. So an interpretation of a decision is going to be like this. In the root node, you have, let's say, a query on the age. Let's say you ask, is the age smaller than 40, higher than 40? But then you have the next node and you say, yeah. Depending on how you answer, maybe you answered yes to the previous question. Then the next question to ask is, what kind of education you have. So for example, you would ask, did you finish high school? You didn't finish high school. Then you have another level where you are asking, did you finish university? Did you didn't finish university? And so on. So the moment that the tree becomes deeper and deeper, the sequence of queries obviously becomes longer, because you will have a query for each node in the decision path. So even though in principle they are interpretable, that sort of interpretation is going to become quickly very tedious, very difficult to use in practice if your decision trees are big, are very deep in particular. Another big advantage is that the feature ranking problem is very easy to solve with the decision trees. It's built in the sense that it's very easy to define an importance score for the features, and it's easy to normalize that importance score to make it relative to each other, to measure, in other words, how much each of the feature contributes to solving the problem. Another strength of this method is that it can handle without really much problems mixed data types. So you can have features in your data set that are numerical, and you can have features that are categorical, and decision trees can handle them just as easy, because it can ask with the same sort of effort questions about categorical features, asking answer yes, no to the question, for example, is the color of your car red, as it is easy to ask something about a numerical feature, for example, the amount of savings you have in your account, and you would ask, is it larger than whatever threshold, or is it smaller than that? Another advantage is that you have minimal pre-processing that you need to do on your data before you are able to apply decision trees. So for example, you don't really need to do normalization on your training data set, something that is really necessary for most other machine learning models. And also that's interesting, for decision trees, typically you don't need to do data imputation, because if you have a training data point, or a data point in general, where there is an attempt to make a query on a feature and that data point doesn't have a value saved on that feature, there is a clear understanding such points, do they go on the left branch or on the right branch, and typically it goes to the left branch, whatever that's in your decision tree. Another one strength of decision trees is that it can deal with classifying imbalanced data, so meaning data sets in which one or more classes are overrepresented with respect to other classes in your data set. And the way to do that is you can adjust the class probability. So when you are calculating, for example, the impurity score, you can add in there weights for different classes, so that you have the smaller classes overrepresented in the impurity. So in that way, you are making sure that they have the role to play in the impurity considerations and in the choices for the splits. So in other words, even though there is an extra step, that one of adding weights for your classes, the mathematical framework remains exactly the same. Decision trees typically are fast to train. We are going to discuss a little bit more about this when it goes to ensemble models, and so there is a whole spectrum of how fast they are, but typically they are fast to train if you compare especially to other machine learning models, say neural networks or other ones. Now, on the other hand, on the weaknesses, they do have limited prediction power. They are essentially just giving you piecewise constant predictions. And what I mean by that is, if you think about the queries that they are making, where they are saying, hey, are you on this feature smaller than or larger than? That's essentially splitting the possible values on that feature into two parts. So it splits the entire space of where your data points can be into two halves. You are less than the threshold or above the threshold. Or if it's a categorical feature, again, it splits into two. It's going to be, are you yes or no on this particular feature, whatever the question it is that you are asking in there. So if you think about the data space, decision trees really split continuously. With each node, they make one more split into half for some region of that space. And eventually when it goes, so it kind of splits it into smaller and smaller boxes. And eventually when you get to the leaf nodes, all the data points that get into the box corresponding to that leaf, they get a single value. So everybody in that box, will get a constant prediction. So that's exactly what I mean by this. Is going to give you constant prediction. And sure, I mean, this is done piecewise, depending on how big your decision tree is. You can have many pieces, but still at the end of the day, it's just a piecewise constant prediction. And so, I mean, you don't really have a more sophisticated type of function, to offer as a prediction. This one with the decision boundaries, it's exactly what I explained in describing the type of predictions and the type of boxes that you get, going deeper into the decision tree. Another weakness here is that typically decision trees are unstable, or another way of saying it is that they have higher variance. And so what that means is that if you have small changes in a training data set, that can change the decision tree quite much. And that's also suggesting, and it's another way of saying that they can overfit. They really reflect very closely the training data set as being passed to them. And out of these weaknesses, maybe the biggest one really is this, that they are prone to overfit. And I want to spend some time to discuss about measures you can take to deal with the overfitting of the of such models, so that you can have access to these strengths that they do have. So there are several things that you can do. One is that you do a so-called tree pruning, and that means that you are going to make sure that your decision tree stays small, because by staying small, you ensure that you don't give it a chance to really learn the specifics of your training data set, but rather you encourage it to learn sort of patterns in your data set. So that's the same way of saying that you are doing early stopping. So you don't let it go to the end until you build, you reach only pure nodes as leaves, but you stop it earlier. And there are several ways in how to do that. For example, you can say from the very beginning, when you start training or building your decision tree, you set the maximum depth of the tree. So you are going to start from the root node, and you are going to build more nodes, and you build additional layers in your tree, but you only do that until you reach the maximum depth. And then all the nodes on the maximum depth level, they are going to be made into leaves no matter what their impurity is. Another way of doing this pre-pruning is by saying, hey, you know what, I'm going to set the minimum number of data points in an internal node. So if you get to a node where the data set is actually smaller than these data points, that's not going to be an internal node. Automatically it's made into a leaf no matter what its impurity is. The same thing you can do by saying, hey, I want to set the minimum number of data points that I send to a leaf, and so don't choose a split leading to a node with less data points than this bound. There is another way of dealing with the overfitting, and that's doing post-pruning. The idea here is that after you have built your decision tree, you are going to start analyzing it and ask yourself whether there are parts of your tree, in other words, whether there are subtrees that you could maybe just, remove and replace the entire subtree with just a leaf node. And the key idea is this. I mean, if you take a subtree and you see, how many decisions are still being made in that subtree, that you translate into the idea of complexity related to that subtree. And so the key idea is you are going to estimate whether the complexity of that subtree, which you measure in terms of, for example, depth of that subtree or number of leaves, for example, whether that complexity is justified for the impurity drop that it contributes. And so, I mean, if a large subtree only contributes a small drop in the overall impurity drop, or you can, and in fact more often it's being discussed in terms of training error. So if this large subtree only contributes a small drop in the overall training error, maybe it could be replaced with a leaf node. And you have two different things here that you need to combine into a single measure and follow that measure when you make this decision about which subtrees to remove, what kind of pruning to do. And so on one hand, you have the idea of the overall training error that this subtree really helps to contribute by asking sharper and sharper questions. And on the other hand, you have this idea of the complexity of the tree or size of the tree, for example, in terms of leaves. So here is how the evaluation is going to be made. After your decision tree is being built, you are going to make an evaluation for all internal nodes. So you are going to take one by one. And so when you analyze internal node M, here are the kind of things that you are going to do. On one hand, you want to calculate the training error. And this training error you are going to denote by RTM, and the training error is going to be for the tree that is rooted at M. So in other words, of the subtree, if you want, that starts from node M. So that means that, you check just all the data points that you have, reaching that node, and you go with those data points all the way to the leaves, and then you check, what kind of error you are making on those data points eventually when they reach the leaves of that tree. And you are also calculating the training error and I denote this by R of M of node M if it was a leaf. So here you are saying, how about if I didn't build a subtree starting from M, and how about if M was decided to be a leaf? What kind of training error you would have? And so the idea is when this node M is made into a leaf, then of course, in terms of a classifier, you are going to make a prediction based on the majority class. If it's a regressor, then you are going to make a prediction in terms of the mean of all the data points that reach this node. So one way or another, if you make this a leaf, you know how to make a prediction, and you can calculate the training error of this node based on all these data points in your training data set that reach node M. So, when you calculate these two numbers, clearly you are going to have that the training error R of m is larger than T of m. And I'm saying clearly because obviously, I mean, by taking more, queries, you are making sharper questions, you are splitting your data set. And remember how the splits were done. They were driven by the idea that you are going to have either more pure nodes or you are going to have points that in a regression problem that have values closer to each other. So obviously, by giving more effort and building a tree rooted in M, you're going to have less of a training error. So this relationship is clear, but it's not clear what happens if I take into account the size of the tree. So I'm writing here, but what if the size of the tree, and I denote the size by this, was counted as well. And I come back to this in just a moment. In what way would you count for this, size of the tree? So one possibility is that you are going to introduce some sort of a complexity penalty. And that is, it's the same idea as in regularization. You want to penalize for more complex trees. And so you introduce or you choose for yourself a hyperparameter, and that's going to be a complexity penalty cost. I denote this by alpha, and this is going to be a non-negative value. And the way you are using this, you are going to now define a measure, R alpha, for the tree rooted at M, and that's going to take into account both the training error and the size. So that's going to be the training error over my tree plus alpha times the size of that tree. And so, I mean, you are now facing this decision. Should I prune this subtree? In other words, should I remove it and replace it with a leaf or not? And the way you decide on this, you are looking at the cost before pruning. So if you didn't prune, what would it be? And the cost is going to be this R alpha. So the cost before pruning is going to be exactly this, what I wrote, one line above. But the cost after pruning, so if you decided to do a pruning and this subtree is replaced with a leaf, is going to be, so we said is going to be the training error, and that we had denoted as R of M, plus alpha times the size of the tree, and the size of the tree was in terms of the number of leaves. Now this node is a leaf itself, so the size is 1, so that's going to be plus alpha times 1, so plus alpha. And so your decision is going to be, hey, you are going to, so decision, you are going to say prune node M if you have a benefit out of this. So in other words, just prune it if the cost after pruning is smaller than the cost before pruning. And this translates, I mean, if you just do the math in here, so that's going to be equivalent to, you decide to prune this node if alpha is at least as large as, and it's R of M minus R of Tm divided by the size of Tm minus 1. So here is how it goes now. You have chosen for yourself a complexity penalty cost alpha, and you are now going to calculate the value here, which we call the effective cost of pruning node M. So for all the nodes M, for all the nodes in your decision tree, you are going to calculate this amount here, the effective cost of pruning node M. And the first thing that you are going to do is you are going to just prune the node with the smallest alpha M in here. So in other words, you are going to prune the so-called weakest link in your decision tree. And once you do that, you have a new decision tree. You are going to recalculate all of these values one more time, because the number of leaves is changing. All of these measures in here are changing. And again, you are going to calculate what's the weakest link. And again, you are pruning at that node and so on. One question that you always have to think about is, how should I choose alpha? And this is a hyperparameter. This is something that is not part of the fitting process. So the way you reason about this is that you will have to do some sort of a cross validation. You will have to choose different values of alpha and do this pruning, and then compare the results. And the comparison of the results, remember, the result is a decision tree, and you can compare different decision trees, for example, by their errors on the validation dataset. So the overall process now, when we have this sort of idea in front of us, is going to be like this. Your dataset, as always, you are splitting into training and validation. You can also have a test dataset, and on your training dataset, you are going to build a decision tree in the way that we've discussed over several videos. And then you are going to say, okay, so I would like to prune this decision tree to make it less complex, maybe less prone to overfitting. And I'm going to check what kind of penalty cost is going to give me the best results. And you are going to check a number of values. And for each such value, you are going to apply this sort of procedure that we have on this slide. And that's going to give you, one pruned decision tree for each value of alpha that you are choosing. And then for each one of these trees, you are checking what's their performance on the validation dataset. And the one that performs best on the validation dataset is the one that you select and you go forward with.